So in the last class, we have discussed about the vector operations. So we discussed mainly about the gradient, Laplacian, divergence, and curl operations. So another important thing that we will be covering is the coordinate system. So coordinate systems are required for us to design electromagnetic systems and also understand the current available electromagnetic scenarios. So as I said before, we have like a scientist who introduced the coordinate system. He was a French scientist, and he introduced the method of graphically representing a certain point in the space using with reference to certain axes. So coordinate systems can have different like definitions. So we will go through them first. So if we take into consideration the position vector of a certain point in the coordinate axis, we will, so we will call that the position vector. Okay, so if there's a certain coordinate, if there's a coordinate system, we have a certain specific point which we call as, for example, R. We can call this R, and the vector that we draw from the origin to that point we call as the position vector. So with respect to a certain origin, we can define what the position vector of a certain point is. So using that vector, we can find the position of that certain location that we are trying to find. So position vector will be consisting of all the three axes that we are considering at a certain point. If we are considering x, y, z Cartesian coordinate plane, then the position vector will be defined based on x, y, and z parameters. So there are x, y, z values can vary depending on the location of the position of the point. So depending on the coordinate axis we are selecting, the parameters that we use to define the position also varies. If we are selecting cylindrical coordinate systems, then we are using magnitude, that means R phi and Z. That means we are using the magnitude of the magnitude to the point that we are selecting, considering, and the angle to the point, and then we are considering the height to the point to define this position of the certain point that we are considering. So another definition is line element. So if these things are not clear to you, please let me know in the chat, or you can let me know. So these terms are kind of specific terms that are used in physics and electromagnetism and in that area. So we will be using these terms in the lectures, and therefore we might need to get familiar with these terms. So the term line element means the displacement vector from a certain point x, y, z to a certain point with a infinitesimal increment, right? So I will explain that in another slide. Anyway, the displacement that occurs from a point xyz to x plus dx, y plus dy, z plus dz can be shown using a certain vector. That vector we call line element. And then we have surface area element. Surface area element is the like product between two perpendicular components of this line element, right? So surface area element is connected to the line element. Whatever the components of line element, we can take those line element components, and we can take the product between each of the two pairs. Right, so I will get to that in another slide. I will explain to you via a certain diagram. And volume element is the volume that we can create when we are moving a certain infinitesimal distance from a certain selected point to another point, and the volume element is taken by taking the product of three orthogonal components of the line element. Okay, so let's see whether there's a diagram already. I think I will take another separate slide and I will explain to you how we can visualize these elements. The position vector, we can I think we can understand position vector, right? So therefore position vector is something clear. So line element, surface element, volume element, I will explain. So if, for example, let's assume we are at the origin and we walk a small distance of dx. We walk a small distance of dx along the x-axis. This is the y-axis, is z-axis. Then we also walk a distance of dy along the y-axis. Since we are now here, we need to go parallelly along, parallel to the y-axis, a distance of dy. Right? So remember, we are only going a infinitesimal distance at along each axis. Infinitesimal distance means we are going a very small distance along that certain axis. So the very small distance we define using dx. Very small distance along y-axis we define as dy. And then we have to go very small distance along z axis. So we go dz along z axis. Z axis is perpendicular to both x and y plane. Therefore, we need to draw it vertically upwards. Then the total distance that that we have traveled is can be given. The total vector can be given using the vector that we can draw from the origin to the point, to the last point that we have stopped. So this vector from the origin to the destination point is known as the line element. Okay, so dl is the notation we use to denote the line element vector. So line element vector we can use, we can denote using dl vector notation. Okay, so can you tell me how we can write this dl vector in terms of dx, dy, and dz? If the unit vectors along x axis is I hat, this is j hat and k hat, can you tell me what is the vector dl in terms of dx, dy, and dz? Why is there a square in your distance, you mean? You are meaning distance. So I asked about the vector actually. Yeah, magnitude we can take as the square root of all those components. Square of all those components. We'll get to that later. Anyway, the vector can be written like this. Do you agree with me? Is this correct or is this wrong? Can you tell me? Is this correct or wrong? I mean, we can denote a vector from origin to a certain point in the coordinate axis coordinate axis space using set of ij, uh, and k hat vectors, right? So this is the way we can denote the dl vector. Yeah. So the magnitude of dl vector, yes, we can denote that using the square root of dx squared plus dy squared plus dz squared, right? So this we can denote. And so this is therefore the line element for the Cartesian coordinate system. Anyway, this is something, this is what we call as the line element. Right? So for each coordinate axis, we can do the same thing. We can go a certain infinitesimal distance along the coordinate axis that is considered, and then we can take the sum of the total the increments that we have made along each axis, and then the final position vector that we can take from the origin to the last destination point is known as the line element. The line element we can denote using the unit vectors along each of the orthogonal coordinate axis that we are considering. Okay, so that is the line element. The line element is taken by going an infinitesimal distance along each of the axes that we are considering, and then drawing the vector from the origin to the last, I mean, destination point, not from the origin, right? From the point we started going, right? So the point of reference. So in here we have taken origin as the point of reference. Therefore, we have taken the line element from the origin to the end point. Right? Is that clear? If it is not clear, please let me know. So if, for example, we did not start from origin, we started from somewhere in between, then we need to take the line element as the line, as the vector from the initial point to the ending point or the final point, right? If we started going from this point to another point in the space, then the line vector will be this. The line vector will be this. That means that if we started going from here to another point, an infinitesimal distance, a very small distance, then the line element will be the vector which is from the initial point until the end point or final point, right? So this could be x, y, z point. This could be dx plus dx plus x, dy plus y, and dz plus z, right? So this point could be the point that we reach once we move an infinitesimal distance along the x, y, and z axis. So I hope it is clear to you. If it is not clear, please let me know. Then we have another definition which we call as the surface element, right? So for that, I will try to erase these. Right. So once we have a kind of a path going from the origin, like as we said, now we have gone through a certain path along the x, y, and z planes. So this path can form a 3D shape. So we can draw a cuboid using this path. We have traveled dx distance, then we have traveled dy distance, and then we are traveling dz distance. Right? From this, we can create a 3D shape. Right? So that 3D shape, we can actually extend our our traveling our travel by projecting our vectors onto the respective axis. So like this, we can create a certain closed, shape, kind of 3D shape, by taking the total distance or total journey that we have taken from the origin to the end point. So this is the end point. So this is the cuboid that we can create. So each of the faces of the cuboid will have a certain area, right? So surface element means each of those areas, right? So we can actually define surface element by taking the area of each of these faces, right? So in this case, surface element can be taken as dx dy, or there are three surface elements, dx dy or dy dz or dx dz. So there are three surface elements that we can define for a Cartesian coordinate system. Then volume element we can take as the product of all the perpendicular elements of the line element, right? So in the definition, we have defined that surface element is the product of perpendicular elements of the line element. So these are the perpendicular elements of the line element, perpendicular components of the line element, and we have taken the product between two of those components. So we have created three surface elements based on that. So volume element, what is the volume element? Volume element of this shape. Can you let me know? Volume element comes from what? By taking the product of each of these perpendicular components. So taking the product of all the components, dx, dy, dz, we can find the volume of the smallest element that we can define for the Cartesian coordinate system, right? Volume element is the element that we can define, and the smallest volume element we can define for the coordinate system. The surface element is the smallest surface area that we can define for the smallest volume in the coordinate system. So there are different surface elements that we can define based on the different sides of the volume. Anyway, the volume element will be the product of all the perpendicular components of the smallest volume we are considering, which is dx, dy, and dz. So if this is not clear to you, please let me know. Those are the actually definitions of volume, surface, and line element that we can define for a certain Cartesian or any type of a coordinate system. So the same thing is shown in this diagram as well. So there's another definition that I actually did not mention to you. I will mention to you that in the next slides. So coordinate systems, when we take coordinate systems, there are basically three types of coordinate systems that we are taking into consideration. So we in this class, we will be focusing on Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. So in this case, like, what is the reason for learning about these coordinate systems? You might ask, what is the importance of learning these things? So when we take especially electromagnetism is working um, along uh, multiple, I mean, surfaces. Right? So in electromagnetism and in physics in general, we are observing some electric fields, magnetic fields varying along the space. So when we are considering certain surfaces and when we are considering electric field and magnetic field in that area, then we need to find out what is the total electric field in that certain area. And if there's a certain closed surface, what is the total electric flux or electric field across that closed surface? In order for us to find that, we need to find the total electric field that is perpendicular to that certain surface. If that is the application, then we need to take the surface element of that coordinate system, and then we need to take angles with respect to the certain other vectors, and then we need to do the computational like dot product and cross product operations. So these things will be done in the certain coordinate system that we are considering. So it's very important for us to select the correct coordinate system for our application. If we select the wrong coordinate systems, we might lose a lot of time trying to solve the big problem. It could be very complex problem if we select the wrong coordinate system. If we select the correct coordinate system, we can really easily solve a certain problem. So depending on the situation, we need to select the correct coordinate system. So therefore, we need to learn the definitions of each of the coordinate systems in order for us to use them in the certain applications that we consider. So depending on the application type, we can use the specific coordinate system. So when we talk about Cartesian coordinate system, as you are very familiar with Cartesian coordinate system, I think I do not really need to emphasize the importance of coordinate system, because can be used in any kind of situation, and it can relate to any kind of a I mean, other coordinate systems as well. We can find the relationship between Cartesian coordinate system and any other coordinate system as well. So there always lies a relationship between other coordinate parameters and Cartesian coordinate parameters. So because of that, we always have the advantage of converting from one coordinate system to another coordinate system using the Cartesian coordinate system and keeping it as the basis. So therefore, Cartesian coordinate system is a very useful coordinate system. So in Cartesian coordinate system, we can define the line element, surface element, and the position vector, and so on, right? So let's try to define those things one by one. So position vector of the Cartesian coordinate system. If there's a point in the space x, y, z, what is the position vector of that point? Can you let me know? If we know that the unit vectors along each of these axes are I hat, j hat, and k hat, what is the position vector that we can write to denote the position of the point that we consider? Let's assume this is a point A. What is the position vector of point A? I need quick answers. Okay, so I think I will give the answer. So x I hat plus y j hat plus k, sorry, z k hat is the position vector of any point in the Cartesian coordinate system. So x, y, z can can be any value. So depending on the value, that point we are considering, you can substitute any value for x, y, and z. And then line element. Line element is the DL vector. And as I defined earlier, DL vector can be defined using dx, dy, and dz components, right? So DL vector we can write as dx I hat plus dy j hat plus dz k hat. And what is the magnitude of DL vector? The magnitude can be taken by taking the square root dx squared plus dy squared plus dz squared. And then unit vector of DL in the direction of DL can be found by taking the ratio between what? So actually you need to give some answers. So we can take the unit vector along the direction of DL along the DL vector as DL vector divided by the magnitude of DL vector. Right? So the magnitude of DL vector we have already found. So the ratio of these two components will give us the unit vector along that DL vector. So we can write like this. We can write like this, the unit vector. So this is actually quite easy, right? So we can go ahead with that. If you don't understand, please let me know. But from that, as I said before, in LMS, I have uploaded the reference material for this. So you can refer it if you have any questions related to these coordinate systems for further information. However, I think these are the basic things that you need to know to like understand the concepts in the electromagnetism and apply these coordinate system for different applications. The surface area element, as I said before, we can find using the multiplication between the perpendicular components in each of the faces of the surface. I mean, 3D element, 3D volume element that we can define for the coordinate system. So this is the smallest volume element that we can define for the Cartesian coordinate system. Right? Once we have taken the volume element, we can define the surface area of each of the faces of this volume element, right? So we can define each of the areas very easily. So one is dx dy, other is dx dz, another one is dy dz. So these are really easy calculations, right? And then volume element we can take by taking the product of dx, dy, and dz. So volume element we can take the product of all the perpendicular elements and we can define the volume element, the volume of the smallest element in the Cartesian coordinate system, right? Now we come to this very important definition. This is what I did not explain earlier, and it is vector surface area. Vector surface area is the vector that is perpendicular to the surface with a magnitude equal to the area of the surface, right? So I will explain to you again, right? So I will take another like this slide. So we know that we can define a certain volume element for the Cartesian coordinate system. So that volume element we can in that volume element we can define the surface areas of each of the faces, right? So that we can define this right. So like this we can define the 3D um, 3D volume element for the Cartesian coordinate system, right? So this is the volume element. Now, each of these surfaces of the volume element, we can define using the values of each of the sides of the volume element. So anyway, now vector surface area, vector surface area. This is very special. Vector surface area. Vector surface area is like the vector version of the surface area. Right? Surface area we know that we can take by taking the uh, product of each of the components of the volume element. Right? So that means we can take, surface area elements we can take as dx, dy, dy, dz, dx, dz. These three things we can take as surface area elements separately. They don't consider any vector components. In this vector surface area, we consider a certain vector associated with the surface area. Right? So the vector of the surface area, vector surface area of this dx dy area is dx dy, whatever the perpendicular unit vector along the perpendicular direction. Right? So we need to multiply dx dy with z hat or k hat. So this is one vector surface area. Can you tell me the vector surfaces area of the other two surfaces? Right? So vector surface area is defined as the vector which is perpendicular to the surface area of the volume element while also being equal in magnitude to the surface area. Right? So the magnitude of this vector surface area should be equal to the surface area that we are considering, and the direction of that vector must be perpendicular to the surface area. Right? So first we actually consider dx dy component. So dx dy component is this surface area. Right? So what is the perpendicular vector to this surface area? It is k hat, right? So whatever the unit vector along z axis we call as k hat, and that is the vector that is the vector which is perpendicular direction to the dx and dy components. Right? So I can also draw this component as the dx dy component, and what the perpendicular vector is in the k hat direction. So the k hat vector we can multiply with the dx dy to obtain the vector surface area of this dx dy. So we can actually define this surface area, one surface area, one vector surface area like this. So there are two other vector surface areas that we can define. What are the two other vector surface areas? Can you let me know? Is it too difficult for you? If it is difficult, please let me know what you cannot understand, so I will explain to you again. Okay, so I think I will explain what surface areas are. Okay, vector surface areas. The other vector surface areas are dy, dz, multiplied with the perpendicular vector, which is I hat. Dx dz multiplied by the perpendicular vector j hat. So these are very actually not that difficult. Once you follow the pattern, you can just understand it very easily, right? So in here, this figure shows those vectors and the surface area vectors. So surface area vector related to dy dz, they have multiplied with x hat. So in here, x hat means the I hat, or like unit vector along x-axis. And then in here, the vector area of the dx dz component is multiplied with y hat, which is the unit vector along y. And in here, they have taken the vector area as dx dy z hat. Likewise, we can define vector surface areas for each of the surface of the volume element. So this vector surface area is used for multiple applications in the electric field and magnetic field calculations, where we want to find the perpendicular vector uh, to a certain surface. So therefore, please keep these calculations in mind and this kind of visual understanding about the vector being perpendicular to the surface in your mind, so that this is applied in multiple situations in the next like classes. Right, and now we are going to the cylindrical coordinate system. So cylindrical coordinate systems are really important as well. So one application of its importance is when we are using antenna systems. So when we are designing or when we are doing calculations with related to antenna systems, sometimes rather than using the coordinate, I mean Cartesian coordinate system, we can use the cylindrical coordinate systems to easily understand the orientation and the location of the antenna. For example, like in cylindrical coordinate system, we can give like in what angle the antenna is in with respect to a certain origin, and in what height the antenna midpoint is in. Right. So because in the cylindrical coordinate system, we are using three parameters. One parameter is the radius. Right. One parameter is the radius. Second parameter is the angle. And third parameter is the height. So the radius we denote using r, angle we denote using phi, height we denote using z. So using r, phi, and z, we can define where a certain antenna is with respect to certain origin. We can define the r value. That means the distance from a certain origin to that antenna, and the angle then antenna is placed at with respect to the x-axis, and then the height of that antenna with respect to the xy plane. So using those parameters, we can easily give out the location of a certain antenna, for example, and we can easily, like communicate that information to another person. But from that, when we are doing calculations also, rather than using the XYZ axis or the coordinate system of Cartesian, we can use cylindrical coordinate system to simplify the calculations. So that is the basically the importance of the cylindrical coordinate system. So cylindrical coordinate system also has predefined line elements, surface element, vector areas, and volume elements, right? So the line element we can find by taking the vector that we can draw from a certain point to another point in the space when we move infinitesimal distance along each of the coordinate axes. So when we are taking line element, we are moving a small distance along each of the axis we are considering. Okay. So are you familiar with cylindrical coordinate systems? Have you learned about cylindrical coordinate systems before? Have you learned in any of your classes these cylindrical coordinate systems? I mean, it's okay if you, even if you have learned, I will explain these things, but it's just that I want to know whether you know the definitions of the radius, phi, and z. You know the definitions of radius, phi, and z? So I will okay, so I will okay, so you have learned about the polar coordinate systems, right? So I can understand what you're saying, right? So you have learned how to convert XY coordinates into R and phi coordinates. So where is this? Take a empty page. So cylindrical coordinate systems are an extension of the polar coordinate systems. So polar coordinate systems form the basis. So you are very correct, right? You have learned about the polar coordinate system, which is the basis of the cylindrical coordinate system. So with respect to x and y, we can define the radius and the phi angle of the position that we are considering. So once we have certain coordinate system with respect to uh, x and y, and then we can consider a certain point which we call as A, and then we can draw the like distance to this place, and that distance we can denote as R, and then the angle to that point with respect to x, from x we are always measuring from x, we call as phi, right? And on top of this, now we are adding z axis. Now we will draw the diagram like this, right? Same thing. The only thing is we are adding z axis, and the point that we are considering could be somewhere here, right? A. And then that point will have an angle of phi from x-axis. Now this is the x-axis, this is the y-axis. And this is the point that we consider, and also the magnitude that we can measure from the origin. This is the origin, is we denote as R. Now this A point is only in the xy plane, right? But now with the addition of z axis, we can even define any point in the space. If we take this point, then we can define that point with respect to R, phi, and z. One important thing is that z is same as the Cartesian coordinate system, right? So you said you know polar coordinate systems. So the only thing we are adding here is the z-axis value, and z-axis value is same as the Cartesian coordinate system value. So therefore, there's nothing like you need to know in addition. You just need to find the height of that position with respect to the xy plane. So if you are considering this point, we can take the projection in the xy plane, and we can draw the line to that point, and then we can draw the angle to that point with respect to x axis. We can denote that using phi like b or something, if we take this point as b, and then the radius value we can write as rb, and then the height we can take using the parallel, I mean distance that we can draw, right? The height from origin to this point we can define as z. So using those parameters, we can define this point in the space. So that is the cylindrical coordinate system definition. And these magnitudes we can define as RB, phi b, and z. So that is the, I mean, definition of cylindrical coordinate systems. There's nothing big, difficult, or different than what you already know. And then we can also write the relationship between the x, y, z axis coordinate system and this coordinate system. So R value we can write as the since r is only related to the xy plane, right? So that also you need to remember, right? R is in the xy plane. It is not in the z plane. R is always defined in the cylindrical coordinate system to be in the xy plane only. Therefore, R is defined as x squared plus y squared square root. It doesn't have z component in it because z is measured from origin to that point. So z is a separate measurement. You only need to take the variation of x and y to decide the value of r. Phi angle is also decided only using y and x. So tan inverse y over x give the angle that we are measuring from x to this point that we are considering, right? So this height is y. So this value is x, right? This length is x. This is x-axis, right? So I think I will erase it just to avoid any confusions. So this is I hat direction. So x, y are the magnitudes along the x-axis and y-axis. So using those magnitudes, we can find the angle tan phi, which is equal to y over x. So inverse of tan of y over x will give the angle that we can form from the x-axis to the point that we are considering in the coordinate system. So I hope that is clear to you. So cylindrical coordinate systems are nothing but an extension of the, I mean, according to my understanding, it's an extension of the Cartesian coordinate system. So the only difference between Cartesian and cylindrical is that the xy plane has been replaced by r and phi parameters. The xy coordinates have been replaced by r and phi parameters. R and phi parameters can be defined using xy coordinate system coordinates as well, right? So likewise, there's a very slight difference between those coordinate systems. So is there anything you want to clarify at this point? So these line elements and surface element and vector area and volume elements we can define for the cylindrical coordinate systems as we have defined for the Cartesian coordinate system. So the line element, from its definition, it's the line vector that we can form once we move from one point. If we take this is the point A to another point, in consideration, let's take this as the destination point B, right? So from A point, assume that we are moving a distance of dr along the r direction. Now r is the vector that we can form from the origin to the like xy plane actually. Okay, so this final like volume element has been actually lifted up from the xy plane. So like let's assume we are going on a journey. We are starting from origin and then we are starting to move r distance along the r hat direction, right? So the coordinate axis we are now considering is the r hat coordinate axis, the phi coordinate axis, the angle that we measure from the x-axis up to the point that we are considering we call as the phi angle, and the axis that we can create along that direction we actually call as phi hat direction, right? Phi hat is the unit vector along the phi direction. Then we move now after coming to a certain point in the xy plane. We are now moving a height of z along the z axis. Okay, so we are moving a height of maybe dz or sorry. So like let's assume we are moving a distance of z along z axis. Now we are in this position. We are in the point A. After coming to point A, we now decide we want to go a very small distance along each of the axis, right? So very small distance along each of the axis means we have to decide what is the smallest distance along each axis first, right? So what is the smallest distance along the all the axes? Can you let me know what are the smallest distances we can go? How do we define those? What is the smallest distance that we can travel along R? dr, right? Dr is correct. And then what is the smallest distance we can go along the phi angle? Now that is a little bit tricky distance. Now phi is an angle, so keep that in mind, right? So once you are going a very small distance along the phi angle direction, we are going along an arc, a certain arc, right? So if we are having origin like this, if you are having a certain origin, we are trying to measure the smallest distance we have traveled from the original phi angle point that we have to a certain d phi angle point, right? However, like what is the total distance we have traveled here? Is it d phi or something else? Phi plus d phi. So I'm asking the total distance that I have moved from the initial point to this point, right? Phi plus d phi is the total angle. It's true. This is the total angle. Total angle is different from the distance, total distance that I have traveled. R into phi. R into phi is this distance. This distance is R into phi. You are correct. You are in the correct like domain. You need to improve your answer a little bit more. This distance is R into phi. Okay, R into phi is the distance that we move from x-axis up to this point. R into phi. This total distance. Okay, R into, now I'm asking only about this small distance that I'm going. Okay, R plus, now you're saying, I mean, your answer is good. Okay, so R into phi plus d phi is the total distance I have traveled from the initial, I mean, x-axis point, right? From this midpoint, if I'm coming, I'm in this A point, right? I want to go to B point. If I want to go that distance only, what is the total distance? So you can actually subtract those two, right? R into d phi. Yeah, that's true. That's correct. Right? R into d phi gives the small distance that I have gone from A point to the B point. Right? So once we try to move a very small distance along the phi angle, we are actually going R d phi distance, because the total distance is given by the radius into the angle that we have traveled. This is something you learn in your mathematics class earlier, right? In your mathematics class, you learn that the angle is equal to the radius into the angle that we are considering. Sorry, the distance, the arc distance, arc length is equal to the radius into the angle that we are considering. So coming back to where we started, so first we need to actually start our journey from a certain initial point. Now we are moving a dr distance, right? We are moving a dr distance, and then we are moving, we can move in any direction, right? We can move along the phi direction, right? So we are moving along the phi direction, right? Now again you will ask another question from me. Now how can we say this r d phi is equal to this distance, right? Because once the radius is increasing, again we need to take r plus dr into d phi as the total length here, right? R plus dr, sorry, yeah, r plus dr is the new radius from this endpoint to the origin, right? I don't know whether you are following me. So this total length into this angle is what r plus angle is what gives the total distance that we are traveling here. And then we go a distance of dz along the z axis direction. And this will give us the total distance that we have traveled along each of the axes in a very infinitesimal manner. So this is the line element that we can define. Anyway, in general, we are only taking r d phi as the length that we have traveled along the phi axis, right? So we are actually not considering a whole journey. We are only considering that we are staying in one position, and then we are moving a dr distance along this direction, and then we are moving r d phi direction in this direction, phi hat direction, and then we are moving dz along k hat direction. And then we are finding, okay, the sum of those three vectors will give us the total uh, line element, or the total sum of the vectors, right? Okay, so that is how we can define the line element, right? So for the line element, so this is how we are defining the line element. The total distance, I mean total line element we are taking by taking the smallest line elements along each of the coordinate axes. So the dr distance along r hat direction, r d phi distance along phi hat direction, right? And then dz distance along k hat direction. So once we are moving that infinitesimal distance along each of these coordinate axes, then we can take the sum of all those components and we can define the line element, right? So in this case, we do not take r plus d phi. We do not take r plus d phi. We do not take like this, right? So we need to be careful. We are not going to add a radius to an angle like this. So, I mean, we cannot add because there are two different units. Angles must be added to another angle. If we are multiplying r d phi, then it's fine. It's totally fine, but we can't add those. We have to be very careful when we are writing these. And if we do addition, then it's wrong, right? So we will have to use r d phi, right? So dr r hat plus r d phi into phi hat plus dz into k hat. That is how we can define the line area. Surface area element we can define by taking the perpendicular, product between two perpendicular components in the line element, right? Line element has three, components, right? Along r hat, phi hat, and k hat. So those three components, the magnitude of those three components can be taken separately. We can multiply two pairwise. We can multiply, and we can find three surface elements, right? And then once we have decided the three surface elements, we can multiply each of these three surface elements by their perpendicular unit vectors, right? So the surface areas of, surface elements are like this, right? So these three elements are surface elements, and the vector areas of those surface elements we can write easily by considering what is the perpendicular vector to this surface area. We can multiply with r hat. The another vector area is dr dz and phi hat. Another vector area is uh, this one into z hat, right? So we can write like dr r d phi into z hat. You can order these things differently, and then you can write them in the correct manner, or in a proper manner by taking r to the front, then writing dr, d phi, and z hat. Then we can finally also write the volume element. Volume element is the most easiest one. You just need to take the combination of all the perpendicular elements, take their product. So the perpendicular elements we are considering in this is dr, r d phi, and dz. We just need to take the product between those three elements. Right? So that is how we can define the volume elements for the cylindrical coordinate system. Right? So do you have any questions regarding that? If you have any questions, please let me know. So in this figure, they are saying that now, even I mentioned to you, when we are taking a smallest element in the coordinate system, we can see that this length RD phi is different to this outer uh, edge distance, which is R plus dr into d phi. This outer, arc distance is R plus dr into d phi. Right? Inner arc distance is R d phi. So R is not the same in all the systems. Yes, it's a very good question. So R is in cylindrical coordinate system is different to the R in spherical coordinate system. We will get into that in the next coordinate system, right? So R is defined in the cylindrical coordinate system as the R that we can draw from origin to the XY plane point that is corresponding to that position we are considering. So this, the magnitude from origin to the position we are considering over the XY plane, we call the R value, the magnitude along the XY plane of the certain position we are considering, we call as the R value. So this R value is actually equal to the polar coordinates R value. Those are same. But is that what you wanted to ask or something else? Because we can consider now in spherical coordinate systems, I will show you this R value is different. Now this R value is the total, magnitude we can draw from origin to the position in the space, which could be a combination of X, Y, and Z coordinates. This point that we are considering at a certain time has the effect of both X, Y, and Z coordinates. Therefore, will be different and will not be the same R as in cylindrical coordinate systems. Right? So spherical coordinate system will be different than the cylindrical coordinate systems. Right? So in spherical coordinate systems, we have the phi angle that we can define, that we can use to define the angle that we can draw from the x-axis up to the point in the xy plane that will correspond to the point in the space. Now, if we take this as a C point, we can project this to the xy plane. That specific point will be taken as the end point of the angle, and we can draw the angle to that point from the x-axis. That angle we call as phi. So this to the angle to this point we can call as phi. Then we need to move another height to the space. However, that height is defined using the theta angle. By defining a certain theta angle from the z axis, we define what is the we call this as using a specific name. I think azimuth angle or axis angle, one of them. So azimuth angle is the angle phi. So you need to check it further. This theta angle, however, provides the third knowledge or information about the location of the point that is considered. So by using that theta angle also, we can exactly position the point in the specific place. We don't have any uncertainties about the final position. So basically cylindrical spherical coordinate systems are defined using these three parameters. So we can define line elements, surface elements, and vector surface areas, volume elements for the spherical coordinate systems as well. So I think I will do that in the next class. So I think some parts of the coordinate systems of cylindrical coordinate systems, I mean, since we were talking about cylindrical coordinate systems, I will try to explain a little bit further about these contents. So we can actually relate the coordinate systems using some relationships between them. As I said before, a cylindrical coordinate system is very related to the polar coordinate systems in the xy plane, and the addition is in the z axis. So we can write r of the cylindrical coordinate systems as x squared plus y squared square root. If I'm wrong, please let me know. Okay, so this is tan inverse y over x, and this is z. So z is same as the Cartesian z. So there's no difference between z. So z is same. Z is same. R and phi are defined using x and y only, because r is in the xy plane. So it is only depending on the values of x and y. So if you have any confusions about that, please let me know. Apart from that, we can define unit vectors along the along the cylindrical coordinate axis using Cartesian unit vectors. So that is defined um, by actually these are very mathematical things. So by taking the combination of the unit vectors along x and y axis, we can define the unit vector along r coordinate. R coordinate. So we can do that by taking now r hat we can define as the combination of cos phi I hat plus sine phi j hat. So we will go to the next slide. So I will show you. This is the unit vector that we can define for the r hat and phi hat unit vectors, right? So the r hat and phi hat unit vectors we can define using Cartesian unit vectors. So Cartesian unit vectors are basically I hat and j hat, and r hat unit vector we can draw, right? We can draw the unit vector r hat. Since now r hat is a unit vector, it is magnitude is 1. Therefore, once we are taking the, magnitudes into consideration, the magnitudes will be 1. So this is cos phi, right? This is cos phi. This length is cos phi. This length is sin phi. And this direction is in the I hat direction. And this length's direction is in the j hat direction. So we need to take the combination of cos phi I hat plus sin phi y hat, j hat to form r hat. R hat is equal cos phi I hat plus sin phi j hat. Likewise, we can find the value for phi hat also. Phi hat is a little bit different, right? Little bit different, but it is also possible. Phi hat is in the tangential direction to the phi, right? So phi is measured using from x-axis up to the point that we are considering. So since this is the angle, we need to take the tangential direction as the unit vector direction. The unit vector direction we can define like this. Anyway, the length of the unit vector we can define using the angle that we can draw in here, right? So the angle we can actually take the alternative angles. This is phi, and this is 90 over phi, 90 minus phi, and this is phi. This angle is phi. So whatever the this distance that we can define. So since this magnitude is phi hat sine phi hat. So sorry, I will. This is sine phi. This is cos phi. So cos phi is in the j hat direction. Sine phi is in the minus I hat direction. Right? So therefore, phi hat I can write as minus sine phi I hat plus cos phi j hat. Right? I hope it is clear to you. Right? So phi hat is a unit vector. Its magnitude is 1. Therefore, once I take the magnitude of all these sides, I can take that magnitude is 1 into sine phi. Right? The magnitude is sine phi in here, but then that is sine phi, and then magnitude along the y-axis direction is cos phi. Right? 1 into cos phi. Then when I'm going to define that those magnitudes and with respect to I hat and j hat, then I need to go along j hat and then minus I hat to reach the phi hat. That's another way of looking it. Anyway, we can define the I hat direction's magnitude as minus sine phi I hat, because our direction of I hat is in the axis direction. So we need to take the minus sine phi I hat. I hat is always in this direction. Since we have to take the other side direction, opposite direction, we are multiplying by minus sine phi and I hat. So we are multiplying by a sign, minus sign, to get it to the correct direction as I hat. And then we also add the y axis component, which is cos phi j hat. So with that, we can define r hat and phi hat unit vectors. The z hat unit vector remains the same as k hat. So since it does not change with the Cartesian coordinate system. So I hope that is clear to you. So I think I will explain the spherical coordinate system in the next class. Magnitude of phi hat. Phi hat is the, unit vector along phi, no? So like unit vector magnitude will be 1. Phi hat magnitude will be 1. Now don't confuse it with the earlier explanation that once we are moving a small distance along phi hat, that small distance is r into d phi. If you're asking about that, right? So now if you are in this position, let's take only the xy plane. If you are in this position, when we want to when we are defining the unit vector along this phi angle, we denote it using phi hat, and the magnitude of phi hat will be 1. Magnitude of phi hat will be 1 because it is the unit vector. Unit vector definition, by definition, its magnitude is 1. And the angle that we can once we are taking a separate scenario where we are moving a small distance along the phi direction, then that distance is defined using uh, like r d phi distance. This is the distance, and along phi hat direction, right? Okay, so thank you so much. With that, I hope you understood some thing, and also I hope you will understand the coordinate systems well. So thank you for attending today's class, and if you have any questions, you can email me, call me. I will be answering your questions. So I will end today's class now. I will continue from next week.